The objective of this topic is to examine the effects of process variables like current, machine settings, shielding gas, and electrode tip geometry on the welding arc.
We'll review the welding characteristics of direct current and alternating current, as well as the role of high frequency in starting and maintaining the arc.
We'll look at the difference between conventional AC, conventional square wave AC, and true square wave AC produced by inverters.
We'll also look at the effect of power source controls like pre-flow, post-flow, AC balance, amplitude adjustment, and high frequency intensity.
We'll examine the effects of argon and helium on the welding arc, and we'll look at the importance of electrode selection and preparation to arc performance.
Gas tungsten arc welding requires a constant current power source capable of producing direct current and alternating current. GTAW power sources are also equipped with high frequency to aid in arc starting.
When the current control switch is set to direct current electrode negative, current flows from the electrode to the work along with about 70% of the heat. DCEN produces the deepest penetration.
When the current control switch is set to direct current electrode positive, current flows in the opposite direction, and about 70% of the heat is focused on the electrode. DCEP is seldom used for TIG welding. For one thing, it produces shallower penetration compared to DCEN. For another, DCEP requires a larger diameter electrode than DCEN because 70% of the heat is focused on the electrode. For example, when the machine is set to DCEN, a 3/32 inch diameter alloyed electrode can carry between 150 and 250 amps. However, with DCEP, that same electrode can carry only 15 to 30 amps.
For direct current applications, the high-frequency switch is set to the start or automatic position. Some power sources set the high frequency automatically when you select the polarity. High frequency assists with arc starting by creating a path from the electrode to the work.
Some machines have a high frequency intensity control. The intensity control regulates the amount of high frequency in the same way that a volume control on a radio controls loudness. Typically, the intensity control is set about midway between the high and low values.
When the current control switch is set to AC, the current alternates between electrode positive and electrode negative. AC is used for aluminum and magnesium. The electrode positive portion of the cycle cleans away the oxide coating, while the negative portion of the cycle provides heat for welding.
There are three types of power sources capable of providing alternating current. Older style transformer rectifiers that produce a conventional AC sine wave, newer generation transformer rectifiers that produce conventional square wave AC, and inverters that produce true square wave AC.
Conventional sine wave AC has a frequency of 60 Hz or 60 cycles per second. Each cycle is balanced or divided equally between electrode positive and electrode negative.
Conventional sine wave AC is inefficient because very little of each half cycle is spent at peak cleaning and welding amperage. If we slowed the AC cycle down, we'd see that a light bulb spends most of its time growing brighter or dimmer, and at the midpoint of each cycle it goes out altogether, but it spends very little time at peak brightness.
The same thing happens with the welding arc. Much of the cycle time is spent ramping up to or down from peak amperage, and the arc extinguishes at the midpoint of the cycle as the current changes polarity, resulting in arc instability. Since the arc extinguishes and reignites 120 times per second, the high-frequency control is set to continuous, so that high frequency is always present to help with arc starting and to stabilize the arc. The high-frequency control should be set just high enough to aid in arc starting.
Conventional square wave technology was introduced in the 1970s. Conventional square wave revolutionized gas tungsten arc welding because it digitally processed the AC cycle to eliminate the gradual transitions between positive and negative half cycles. The end result is a smoother arc because the change from positive to negative is instantaneous, and the arc is more efficient because it spends more time near the peak cleaning and penetration portions of the cycle.
Another advantage of conventional square wave technology is the ability to unbalance the AC cycle. By turning the balance control toward cleaning, you can lengthen the percentage of electrode positive up to 55% of cycle time to provide more cleaning action. And by turning the balance toward penetration, you can lengthen the percentage of electrode negative up to 68% of cycle time to provide more penetration.
An arc that's adjusted for more cleaning action will produce shallower penetration, and the electrode will have a slightly larger bald tip due to the increased amount of time that the electrode is positive. The ideal balance uses as much electrode negative time as possible, with just enough electrode positive time to keep the puddle shiny and clean. This puts more heat into the work to produce the desired amount of penetration, and less heat into the electrode, which prevents excessive tungsten balling.
Inverters provide several advantages over conventional square wave machines. Inverters provide more precise balance control. For example, you can increase the electrode positive portion of the cycle up to 70% of cycle time, compared to 55% on conventional square wave machines. And you can increase the electrode negative portion of the cycle up to 99%, compared to 68%.
Conventional square wave power sources operate on a standard line frequency of 60 Hz in North America and 50 Hz in Europe. With inverters, you can vary the frequency from less than 60 Hz up to several hundred cycles per second. A frequency below 60 Hz provides a soft, wide arc with a wide weld bead, a wide cleaning zone, and shallow penetration. As the frequency increases above 60 Hz, the arc cone becomes narrower and the arc pressure increases. This provides a more focused arc with deeper, narrower penetration and less arc wandering.
Some inverters also allow you to adjust the amplitude of the electrode positive and electrode negative portions of the cycle independently. The resulting waveform is called asymmetrical. This allows you to provide just enough electrode positive amperage for adequate cleaning, and the right amount of electrode negative amperage to produce complete penetration.
With the right combination of balance and frequency, you can weld without continuous high frequency because the arc is so stable. And depending on the amplitude of the electrode positive portion of the cycle, you can weld with a tapered electrode. The end result is pinpoint precision and narrower heat-affected and cleaning zones compared to conventional square wave technology.
Some power sources are equipped with upslope and downslope controls that are used in conjunction with automatic applications. Upslope produces a softer arc for arc starting by allowing you to adjust the time it takes amperage to increase to the high current setting. Downslope is a programmed reduction in the amperage to compensate for heat buildup and to allow for crater filling.
Gas tungsten arc welding uses an inert shielding gas to protect the weld puddle, filler rod, and the electrode from oxidation during welding. Argon is the most commonly used shielding gas, followed by helium. Argon and helium are often mixed in different ratios to produce specific arc characteristics.
Argon has a lower ionization potential than helium. Ionization potential refers to the amount of voltage required to turn the shielding gas into an electrical conductor. Lower ionization potential results in easier arc starting. It also provides a more stable arc, especially at lower amperages. This makes argon excellent for thin gauge metals where low heat is necessary to prevent excessive penetration and burn-through. Argon provides better cleaning action than helium, resulting in superior weld appearance.
Argon also produces a more focused, pinpoint arc than the bell-shaped arc column produced by helium. And argon is heavier than air, which means that it remains in the arc area longer than helium when the puddle is below the nozzle.
Helium has a higher ionization potential than argon, which means it takes more voltage to ionize the arc column. This makes arc starting more difficult. Higher voltage also means that amp for amp, helium produces a hotter arc than argon, which allows you to achieve deeper penetration and faster travel speeds. This makes helium well suited to thicker sections, especially thicker sections of aluminum and copper.
Argon and helium are often mixed to take advantage of the best that both gases have to offer, like easier arc starting, better arc stability and cleaning action, a more focused arc cone, faster travel speeds, and deeper penetration.
As we saw earlier, pre-flow and post-flow are critical to producing a quality weld. A small amount of pre-flow ensures that shielding gas is present for arc starting. Post-flow allows the molten puddle and superheated electrode to cool before they're exposed to the atmosphere. A good rule of thumb is to allow 1 second of post-flow time for every 10 amps of welding current.
A high-quality tungsten electrode is brittle. It should snap when you try to bend it, indicating a fine grain structure. Poorer quality electrodes tend to develop longitudinal cracks that can cause the arc to wander.
Tapered electrodes are used for DCEN applications. The angle of the taper, called the included angle, affects the shape and penetration characteristics of the welding arc. Typically, the taper should be about 2.5 to 3 electrode diameters long with a 1/64 inch diameter flat ground at the end to remove the point. For very low amperages, you may not need to remove the tip.
Pure and zirconiated electrodes are used for alternating current when you're working with conventional square-wave power sources. Pure tungstens are the least expensive, but they have about half the amp carrying capability of alloyed tungstens. This makes them prone to tungsten spitting, which may result in tungsten inclusions in the weld. So zirconiated tungstens are used when X-ray quality welds are required because they can withstand higher amperages and are less prone to tungsten spitting.
Pure and zirconiated electrodes for use with conventional square-wave power sources should have rounded tips equal to the diameter of the electrode for best performance. If the tip becomes too large, it produces an erratic arc that dances around the surface of the ball.
However, inverters allow such fine adjustment of the amplitude, balance, and frequency of the AC cycle that you can use any of the alloyed tungstens for AC welding. And unlike conventional square-wave machines, you can use a tapered tip with inverter AC because the current will define a ball at the tip of the electrode suitable for the application.
There are a variety of tungsten grinders with diamond wheels on the market. Tungsten grinders are the best way to ensure precision grind because you can set them for the desired included angle and tip diameter.
Gas tungsten arc welding is one of the most challenging processes to master because it requires good hand-eye coordination, as well as a knowledge of what the controls on the power source do and how you can adjust them to produce the desired results. So take some time to experiment with different machine settings to see how they affect arc performance and the quality of your welds.